All right, guys. Today we're going to go through just a quick set of notes on velocity and acceleration. I know we've talked about most of this extensively, so it should be just a quick review. But just wanted to make sure we still had some formal notes on distance versus displacement, velocity versus speed, and then velocity versus acceleration. Kind of how all those things relate to each other and compare to each other. So we know for motion that everything in the universe is moving. How do we know that? Well, we know that the Earth is moving, it's rotating about its axis, it's revolving around the sun. The solar system is revolving around the galactic center, and the universe is ever expanding. So, oh, hey, look at that. I had all that stuff already stated, so going through quick. Motion is also relative, not someone you're related to, but Einstein's version of relativity, where if we're talking about the motion of an object, it has to be in comparison to some other object, some reference point or reference frame, where if we have, if I'm holding a ball and right now to us it looks like it's sitting still, that's the motion compared to the reference frame of this room or us. But we know that that ball, if I was holding it, it's actually moving because the Earth is rotating. Again, it's revolving around the sun. It's revolving around the galactic center. The universe is expanding. So there is still motion of it, but we don't say that it's in motion because relative to our frame of reference, which would be the room we're in, it's sitting still. Notes-wise, you can take as formal notes as you want to, live and living color. Actually, if you pause the screen right now, this is everything that we'll go through today in this set of notes. So you could even just copy stuff down. It's up to you on how formal or informal you want these notes to be. Most of this stuff right now for this chapter is relatively simple that you probably can do without any issue. But for those that want to take notes and want to organize themselves, that's how I would format it. All right, so jumping into speed first. Speed is the first thing that we think about. It's the measure of how fast something is going. We know that we can calculate it by doing just distance over time. So how far you went divided by how long it took to get there. That's your speed, which is, that's the rate, something divided by time. Our SI unit, so our standard increment unit, that's kind of SI units is what we use standard in science. The standard unit for speed is meters per second because our standard distance unit is meters. Our standard unit for time is seconds. So meters per second is our standard unit for speed. We can measure it in different ways, but that's our standard unit for it. All right, and we've talked about this as well, instantaneous speed versus average speed. It's a little more difficult to measure instantaneous speed. Your car does it for you as you guys are driving. That is the current instantaneous speed that your car is traveling. It doesn't take an average speed over a certain time interval. It's just the instantaneous speed. Right now, that's how fast you're going. Average speed is a little easier to calculate for us observing stuff because all we have to look at is, all right, here's my total distance traveled. Here's the time it took to travel that distance. So we can look at the average speed as doing that. Now, speed versus velocity is a little bit different because speed is what we call scalar, which means the direction doesn't matter. All that matters is the magnitude, the size of the speed, the size of the number. Direction has no impact on how fast you're traveling. You don't say you're traveling 50 miles an hour south. That makes no difference speed-wise than if you're traveling 50 miles an hour north or east or west or anything like that. Velocity, direction does matter. So we could be going forward, backward, left, right. In this case, velocity is what we call a vector value, which our next set of notes that we'll be doing on Friday, we'll be talking about what vectors are and how we use those to describe our some different values. We'll use vectors throughout the school year. Here in velocity, we'll talk about vectors again next chapter in two-dimensional motion, so projectile motion. We deal with vectors when we're talking about forces. There's a lot of different places where we use vector values. So again, here just a nice little summary of the difference between speed and velocity, getting more into our calculations of them. They are very similar. It's still going to be some length, some measurement divided by time. But we know with speed, we're looking at our total distance traveled. And our velocity, this is where we're looking at just that displacement divided by time. And again, what's the difference between distance and displacement? We know that distance is literally how far you traveled. If you counted your steps and you drew your path along the way of where you went, that's your distance that you traveled. But your displacement is just how far you are from that starting position, which this here is a nice illustration of the distance versus displacement. This is a Family Circus cartoon. So you can see right here at the red arrow, this is where the little boy started. And he's got this whole big, long, dotted line path going all throughout the little neighborhood. And then he's ending right here around the corner. So a very, very, very large distance traveled, because you can see he ran all over the place. But in terms of displacement, from the steps around the corner here is where he ended. So a very, very short displacement. All right, so calculating some speed, let's do an example together. Usain Bolt can maintain a constant speed of 12 meters per second. He will cover 12 meters every second, which is what 12 meters per second means. At this rate, how far will he travel in 10 seconds? So not a traditional problem where we're just given the distance and we're given the time to find the speed. Here, we're going to have to do some equation rearranging. You can do this either before you plug numbers in or after you plug numbers in. Here is kind of the process that I did just all together. So we started with our speed. In this case, we're doing average speed is distance divided by time. So if you wanted to rearrange your equation, since we're trying to find the distance he can travel, we'll solve this equation for d by multiplying by t on both sides. That gives us this, s times t equals d, or d equals st. And then we're just plugging in the speed that Usain Bolt can maintain, 12 meters per second, the time he's running that distance, which is 10 seconds. So when we multiply those together, notice here, the 12 times the 10 gives me my 120. My s, which is my time, and the s in my denominator for velocity, those cancel each other out, which is why we have 120 meters for my answer. Same question here. 12 meters per second is the speed that he can maintain. He will cover 12 meters every second. Again, just reiterating what that means. At this rate, how far can he travel in a minute? So we can use this same equation, d equals st, so distance is speed times time. In this case, we do need to do a little quick unit conversion because we can't just plug in 1 in here because our time is measured in seconds right now. So we have to do that quick conversion from 1 minute to 60 seconds. And you probably don't have to show this formal unit conversion like you did in chemistry, I'm sure. There'll be some later on in different chapters where we will have to take a little bit more time when doing that unit conversion to be able to convert from one thing to another. But in this case, just make sure you remember you have to plug in 60 instead of 1 because our time is measured in seconds, not minutes. So here we should get 720 meters if you were able to actually maintain that speed for a full minute. All right, so acceleration. Acceleration is, you can see up top right here, it's the change in your velocity over the change in time. So very similar to your velocity is your change in position over your change in time. We're just going up to that next level. So acceleration, this is the formula for it. These little triangles, that's the Greek letter delta. That's what we use in upper level math and science to just represent the change in. So in this case, delta V over delta t means the change in velocity over the change in time. There's 3 different ways that we can have an acceleration. We could either speed up or slow down. Those are the 2 obvious ones. That's going to change your velocity. But we also have the option, because velocity depends on the direction you're traveling. If you change the direction that you're traveling, that's going to change your velocity, which means an acceleration happened. So that's our 3rd option down here. Our change in direction is also a form of acceleration. Our units here, since we're looking at the velocity over time, that's meters per second is our standard unit for velocity. Seconds is our standard unit for time. So meters per second squared is what we end up with for our standard unit for acceleration. All right, so doing a problem here, you can see at the bottom, I'll use this phrase kind of throughout the school year. Unless I say otherwise, you should be rounding it to 2 sig figs. So sig figs, that's our significant figures. That's how many places you need to go in your calculation. So in this case, we're taking a look at our car that accelerates from 25 meters per second to 30 meters per second in a total of 2 seconds. And we're trying to calculate its acceleration. So our equation again for acceleration, delta V over delta T. So the way that we actually calculate that is kind of like the slope, and when we're back in the way that we actually calculate this is kind of like how we calculated slope back in Algebra 1 or Algebra 2. We know that the slope of a line is y2 minus y1 over x2 minus x1, because slope is the change in your y value divided by the change in your x value, delta y over delta x. So very similar here, we're going to look at our usually we do this as our final velocity minus our starting velocity over our final time minus our starting time is usually how we label V1, V2. So in this case, our ending velocity was 30 meters per second. Our starting velocity was 25 meters per second. We ended 2 seconds later. We started at the beginning, so at 0 seconds. So you can see here, 25 subtracted from 30 gives us 5 meters per second, divided by 2 gives us 2.5 meters per second, or meters per second squared. So again here, units meters per second is meters per second times 1 over s, which is where we get that from. We talked about that yesterday. I don't remember when we did. When we were talking through it was the first day we were working on the SVA lab. We talked about where that meters per second squared comes from, or ms to the negative second power, different ways we can write it. So that's our answer, 2.5 meters per second squared. All right, gravity, which we started kind of briefly talking about with this most recent lab, with kind of where that acceleration happened or comes from with the ball rolling down the ramp. So gravity is a form of acceleration. It's here on Earth, it's 9.8 meters per second squared is the way that it accelerates. Actually, it's negative 9.8 meters per second squared is what I should have here, because that gravity is pulling down objects, and it causes them to accelerate at negative 9.8 meters per second squared because it's going down, a negative velocity change. Gravity is constant on Earth. It causes the same rate of acceleration for all falling objects, which we'll spend a lot of time on next chapter when we start talking about projectile motion, launching things. We'll talk about free fall and how gravity affects our different objects. But that's all I got for you today. So just watching this video is all you need to do today, so make sure you guys have your notes updated. There's also a worksheet that you guys will be working on. I'll probably post that today, so if you want to start it, but you guys will have class period tomorrow to work on it, just to get those questions answered. So if you have any questions or concerns, feel free to let me know. Otherwise, have a great day. We'll see you guys tomorrow.